Morning, engineers. My name is Lucas Moronge, a civil engineer by profession, and in this tutorial, I'd like just to take you through how we can design or how we can validate our design after we do our analysis. This specifically for a two-way slab, and we are going to do our validation with the assistance of automated manual calculation. That is the use of RCC Excel design spreadsheets for reinforced concrete, as you can see them on my screen. So this is what you are going to use actually to do a validation. So without wasting much time, let's get started. So let's assume you have designed your slab or your any reinforced concrete with the software, and you already have your outputs similar to what we have here. So you can see this slab has been detailed, but how are you sure the software did the right thing? You have to do a counter check. You can actually work out the manual calculation with just a calculator. You can see generally using the 10 at a spacing of 250. Now, let's check if we input the same parameters that we actually gave our software, whether we are going to get the same result in Excel sheet. And that's why I'm here. We're just trying to validate and do a review of already designed members with the software. So the first thing that you do, you have to understand your key parameters that we use. So I've actually table down all the parameters that are used, which is the longer span, as you can see here. So we have this is ly, lx, which now you can get the aspect ratio, very fast aspect ratio, which is 4/5. That's ly over lx. We have the dead load, we have the type of bar that has been used, concrete cover, depth or thickness of our slab, we have the concrete grade, steel grade that has been used. Then what you have here, we can easily get them from our design code. These are the parameters. These one are, you just read them from the BS 8110 table, which is table 3.14, to get these coefficients. So why do we get this coefficient? You want to get what is called moments. So first thing that after you get your parameter like this, the next thing that you do is you calculate your design moment. You simply take your dead load, you factor it with factor of safety so that you can get now your ultimate design moment. And as you can see, we already have the dead load here and the live load. So this how they were calculated. If I may just show you how we got those live load and dead loads. So you can see, just allow me to quickly show you. So to get the dead load, we had to add the self-weight of our slab, also had to add the finishes, and now we had to add the partitions. Now we added all those, the total dead load was 6.1, whereas the imposed load from the BS, we got it as 1.5. Now, once we get that, we now have we can now easily calculate our design moments, not our design load first. So once you get your design load, now you will move to the design moment, because for you to use this Excel sheet, that's Excel spreadsheet, there are some key parameters that you actually have to key in. You have to get this design moment. So how do you get this design moment? You have to calculate it. Now, once you get the design moment, all the other parameters, you can see they're already here and I've already shown you. So let's just show you how to get that design moment, because I think that's the most challenging part of this validation process of our results. Now, how do you calculate it? First, you just come to what is called the table here, so that you can read the coefficient. This is called bending moment coefficient, because the formula that we use to calculate the bending moment, it's here. Yes, this is the formula that we use to calculate the. So remember that L, we have L as the length of the shorter span, which is 3500. It's 3.5. Then we have N as our now design moment, which is 10.94. And what else? So we have to get these coefficients. Now, this coefficient can easily be read in the table that I've actually shown you below here. So let's go to the table, and to read this table we just have to get the aspect ratio, which is our aspect ratio is 1.1 here. We are dealing with one long edge discontinued slab. So let me show you how this condition is obtained. Now you go to check on your boundary condition of our slab. So we just come to this slab. We are using this slab because it seems to be the most critical. Actually, it's the most critical here for this case. So we are using this slab. So you know that you can see this part is enclosed, this part will be enclosed, this part apart from this. So you can say this is one long edge discontinued because this is the longer edge, this is the 4 meter span, and this is the 3 meter span. So if we come here to our, now that you have your parameters, you can now easily come and get the coefficients that you're looking for. So you can get this one long edge discontinued versus the LX over LY aspect ratio 1.1. So we have these coefficients. And now we also have these coefficients here. So having gotten your coefficients, the next thing that now we do, we just go to our calculations here, and then now we just key in and get our moment. Remember that the formula to get our moment is here, as I had just shown you. So if you have your formula as this one, now you have your B, you have your N as your ultimate design load, LX. So if you calculate, now you come and key in your parameters here. But if I may show you just a single diagram on that, let's just move here. So we have this direction, this LX, short span. So this moment here, this MX, then we have MY. So these are positive bending moment at mid-span, but at the supports, we also have negative holding moments. So that's why you calculate both and then you pick the highest moment. So based on our design, or based on our calculation, we are now getting our moments as along the x axis or along the shorter span as 4.42 and 5.8. So these are now, this is the moment that now we use in the Excel sheet that I showed you. So you simply go and key in. So for along the shorter span, we are actually going to use 5.89. We can round it to 6 and round it to 6. And for the longer span, we'll be having 4.9. So we can round it to 5. So let's go to the Excel sheets. It's in a position that can be read. So just key in your moment, you key in your BB is the breadth factor. So we are designing a 1 meter breadth. So you consider as a 1 so that you can get 1 meter run, 1 breadth of whatever you are considering on the slab. Then for the span, we are considering the shorter span, that is LX, which is 3500, we key it there. Slab depth is 150, burden it is 8, and cover is, I think cover was supposed to be 25. Design. So maybe this one is 25, and everything holds. And now here you can actually get your calculation here. And now you can just try to consider. So let's change this one to D10 so that you see. I had already worked out so that I could save time. And if you make D10, you can see D10 can even work at a spacing of 400. spacing of 400, so it will fail on the maximum spacing. So meaning that using the 10 on this slab is kind of over design. So if you use the 10 as a lesser space of less than 400, you are doing what's called an over design. Remember that the required area, as you can see here, it is 195, and the provided area here, it is provided at 400 is 196. Work well, or to ensure that it works well, so you change this one to D8, and if you use D8, you just notice the area provided. So this is the most fairest at a spacing of 250. So this is most okay. You can see deflection is okay, uh, maximum spacing is okay, minimum spacing is okay. So you can actually see this is what actually is okay for that. So if we go back to our design now and we do validation, there is something I want you to note. This is Excel sheet, you can't actually determine the spacing. The Excel sheets determine for you the spacing, the best spacing that you can use. And I think using the 10 at a spacing of 250 is kind of an over reinforcement. You can simply use the 8 and it's going to work. So if I actually now come to my software here, if I review this was done in ProCon. So if I simply come here, and this D10 should be D8. So using D8 can work, and you can save your client some little of cash because you'll use tracer reinforcement to just do it here. By doing that, now you have optimized design. By doing that, now you have done an economical design from a point of information. I hope this was informative, and if you found value in this video, please consider subscribing, like, and leave a comment so that